Good evening and welcome. Welcome to the winter season of virtual science camps. As you might notice, there's not many people yet, so please feel free to ask any questions you want. Stop me because it's not very crowded at the moment. Thank you for joining me. I'm really excited to have you guys back and to share with you this new themed session of particle physics for kids. So I'm going to go over a little bit of that and explain why I've chosen this theme, who the guest hosts are, what we'll cover in some of the sessions, and maybe help you guys decide if you're hesitating on some, if you don't know much about particle physics, maybe you just want to do the sessions that I don't cover many particle physics. So I'll try and go over any of those things this time. And thanks again for being with me. So to explain a little bit about how I chose the theme of particle physics, because I myself was a little bit intimidated by the theme of particle physics, even my first couple of years as a teacher. Like it's something that isn't covered all that much in a standard bachelor's degree. You do have a couple classes on it and whatnot, but it's not a part of physics that I initially really loved or was that interested in. And I only really got interested in it, like to be passionately interested about particle physics, once I'd had the chance to learn from a bunch of particle physicists. And so the plan for today is to spend 5 or 10 minutes to explain like some of the people I learned from, a lot of who will be joining as guest hosts, mainly on Tuesdays, and kind of what will be covered in their sessions as well. So to go over that a little bit, my first time visiting any nuclear research center was in 2018. And how it came to be was sort of a coincidence. I'd received an email from someone at UNESCO inviting me to a roundtable between UNESCO and JINR. And I looked at my calendar, I was free that day. I said, okay, sounds interesting. Let's sign up for it. And I signed up without even knowing what JINR was. And it was only after I signed up, I found out it's the Joint Institute for Nuclear Research, which is based outside of Moscow, Russia. And so I went and I saw a bunch of interesting presentations from particle physicists who are like world leaders in it. There was a talk from Yuri Gaganin, who's the only living person with an element named after him in the periodic table. And after the talk, I introduced myself to some of them. And I explained I'm a teacher and I look for new experiments in different parts of the world. And they invited me to come to Russia. So I went to Russia and I visited the Joint Institute for Nuclear Research. And I've grabbed a couple of photos to show just of my time there, because it was a pretty exciting thing for me. And I am not loading the photos right. Okay, here we go. So you should be able to see me in front of like a synchrocyclotron, although most of you probably don't know what one of those is yet. We'll get to that in a bit. In front of a big periodic table in Russian, because it's in Russia. Notably, notice these last couple elements are filled in with their current names. And if you get an old periodic table, like probably in most textbooks, on most school walls, like posters like that, even a lot of websites are out of date and they won't include these elements because they've been discovered in the past decade or so at the Joint Institute for Nuclear Research. And this is the wall in the room opposite that. And it's a pretty amazing discovery, discovering 10 new elements. And on this graph, which is a graph of nuclear stability, basically that means how easy it is for that type of element to exist. And up here is an island of super heavy stability. And that's what they predicted existed and predicted that they'd be able to make the most recent atoms that they've had. As you'll notice, the graph is pretty dark here, which means that most of the elements here exist pretty stably, and we can find those on Earth. Then there's a bit of a gap, and then a little bit of a peninsula, and then like nothing. And that corresponds to elements that generally don't exist because they're not stable enough to exist. And everyone thought that then that was it, except there were some theories there might be more elements we can discover, and this is what they did there. So it's kind of a cool experience getting to go there And before I went on that trip, I realized that I only knew particle physics up until like a university year 3 level. And to not be embarrassed meeting a whole bunch of particle physicists, I spent a couple of weeks like with textbooks going over particle physics and looking up online so that I'd be kind of up to speed to be near to that level. So even if you've been teaching for like 10, 15 years, there's still a lot more you can learn. This is a picture of me with some Israeli teachers. I joined with a group from Israel, from like a gifted school there. And this is in a control center for one of the accelerators. So we're behind all these, in front of all these monitors here. And we're going to have a couple of guest hosts later on in the month, probably the 26th of January. But those of you who know much about Russia might know that on Thursday was their Christmas. They celebrate based on the Julian calendar, 13 days later than we do. So they're still in Christmas holidays, and I haven't confirmed the dates with them yet. But probably we're going to have a talk from Dmitry. I should have had his name written down in front of me. On the Big Bang and how particle accelerators are looking to study the conditions after the Big Bang. Then going back to CERN, which was the second place that I went, here's a picture in front of like the cafeteria at CERN. You can just barely see Mont Blanc in the background from Geneva. And CERN Control Center, as you can see there. The guy next to me, this is a teacher in Turkey, and you guys may have noticed there's been a number of Turkish students who have joined the camp sometimes. That's largely because of him, like his students, and mentioning it to other teachers in Turkey there. So that's my friend Ozan. And this is the inside of a dipole, which is one of the like main units of the Large Hadron Collider, which is the largest particle accelerator. Oh, and just outside the antimatter factory with Anya, who's going to be a guest host for, I guess, just one session, but Tuesday's session, she's going to be doing a science show called It's Just a Phase. And this is one that'd be great even for younger ones. They were saying they developed it originally for a science festival in Germany where like it was general public, kids as young as like 6 or 7, although that young you might not get all of it, but like no one who's joined the camps has been that young anyways. And just because it's interesting to show that they developed the World Wide Web there, there's a picture of me in front of the plaque in front of Tim Berners-Lee's office. And he was the guy who originally came up with the World Wide Web. And that's a story in and of itself that I won't take time to go into detail, but essentially because they needed to send a lot of information from one nuclear facility to another, then they eventually got to a point where they needed to have a protocol based on which the computers would transfer information. And because that was the most efficient protocol for computers to communicate with each other, that eventually grew into the publicly used World Wide Web. And so
they used it for the army before that, though, didn't they? The ARPANET.
Oh, well, that's a different one. So that was the US military that developed DARPA and DARPANET. And so there's also a lot of kind of confusion whether you talk about the internet versus the World Wide Web. Because unless you look at how it exactly works, a lot of times those are used as synonyms. And CERN didn't develop the internet. That was mainly an evolution of DARPA, but a couple other things coming together. And so it's often missaid that they invented the internet at CERN because they didn't really do that at all. But it gets nitpicky into details saying, well, what's the difference between the web and the internet? And like for most people's purposes, unless you're even if you're making web pages, the difference doesn't really matter. But if you're designing infrastructure, like to look at where is the internet? How's it housed? Like all those details, then the difference between the web and the net comes up as important. But yeah, like not only would it take longer to explain than I want to take, I don't confidently know enough of the details to try and like just make up. I could make up stuff, and most people would believe me. But like rather than making it up, I'll just say it's slightly different, but almost the same. Um, and and so like that, going to these two places, I was inspired by people like Anya, like Jeff, who will be the guest host for the session on the 19th of January. He's the head of teacher programs there. Met a bunch of cool teachers around the world that I shared ideas with. Um, and that's kind of why I wanted to share the same experience with some of you guys through the virtual science camps. Um, the idea that if I was kind of intimidated, hello Eli, welcome. If I was intimidated by particle physics until it was broken down in a simple way for me, then hopefully I can do that for others and like kind of break it down into simple enough steps and have some exciting guest hosts from some of the world's coolest places for particle physics. To briefly mention some of the other guest hosts that'll be joining, there's Luca. Again, I should have written his last name for the list, but you guys probably don't care about his last name. Who's actually a friend of Anya's. So Anya, again, who's going to be guest host on Tuesday with her science show. And before she started working at CERN, she was working at a science museum in Slovenia, where she comes from, Hisza Experimentov, which is a small science museum, but a really cool science museum. And amongst other things, because they don't have a lot of physical space available, then they do a lot of science performance, science stuff on the road, science shows. And Luke is one of the like performers and facilitators there. And he'll be sharing something not on particle physics at all, but it'll be on water and on coins, using it like some of his coin collection from around the world. So if particle physics really isn't your thing, then Luca's guest session would be a good one as well to join on the 23rd of January. That one is. It's not yet on the schedule I've sent out, just because I don't have the details for what materials you'd want to follow along at home. There's also going to be a teacher from the Perimeter Institute in Canada. They're like one of the other top places in the world for theoretical physics. And they have really cool activities. If you joined for the one on exoplanets with Kelly in the springtime, she's an astronomer at the Perimeter Institute. And a lot of the stuff they do, like the types of activities they have, like that one we were modeling exoplanets with a sensor on a cell phone. I'm not quite sure what Dave's going to propose from the Perimeter Institute, but whatever it is, I'm sure it'll be amazing. Yeah, so that covers the guest hosts to expect over the next couple of weeks. And now we'll get to my favorite part. I think probably a lot of your favorite parts, where we'll do a couple of experiments. So I'm going to stop sharing my screen because I don't need any pictures of me anymore. And the first couple experiments, there'll be a preview of the phase changes in the kitchen, which will be a week from now on Saturday. So the first thing I'm going to do, and I don't think I asked you to grab any of the materials for the phase change one. I think I just mentioned magnets, which will be for an electromagnet one on the 30th of January, Saturday, the 30th of January. And the reason for the phase change ones, I'm just going to show you rather than ask you to try and do it at home. It gets a little bit messy, and one of them uses acetone, and people get a little bit funny about acetone in France. It's a substance, there's a couple of substances, country to country. People have completely different ideas on the safety behind it. And in France, it's generally considered very dangerous. You shouldn't have kids use acetone in any situation. If we were in North America, it would be considered perfectly safe. Everyone can use it. No one would drink it. But so for that, I'm not telling you to follow along with this one. So
What's
the
it
first
called
one.
in French?
What's that?
What's it called in French?
Acetone, it's the same word in French, except it's just pronounced French, like acetone.
Okay.
But like, I'll show you the bottle too. And if your parents are okay with you doing it, like feel free to do this one at home afterwards. Like this is how it comes in France. And I just got this from, I don't know, maybe Franprix or probably Carrefour, but like any grocery store will sell it. But yeah, check with your parents before using this, just because, especially if they're French, they probably won't want you using it. And you could, maybe for good reason, maybe not, but like it is toxic. It's bad if it gets in your eyes. But what I'm going to demonstrate with that one, I have a balloon, just a regular balloon that you'd fill up with air, only it's filled with a little bit of acetone. And I'm going to take some water that I've boiled ahead of time. And I'm just going to dump it on there. And leave that for a couple seconds. And we should see a phase change. The acetone will turn from liquid to gas. And the gas form will take roughly 1,000 times the volume of the liquid form. So if the phase change is complete, the balloon will get very big. If the phase change is somewhat incomplete and it takes a little while for the acetone to absorb the heat from the water, then it'll probably only get like medium big. But it'll be demonstrating the difference in volume between the two. As I leave that for a sec to keep getting bigger, I'm going to grab a giant ice cube from my fridge. And we can see it's starting to inflate. And I'm just going to heat up some water even hotter. Meanwhile,
what is that?
This one here, this is a balloon with acetone in it. So when we started, it was all shriveled up and small. And now that the acetone is absorbing the heat from the water, it's changing phase and it's boiling, because the boiling point of acetone is about 50 degrees at regular pressure. With the pressure of the balloon, it's actually a little bit higher. So the temperature's got to be raised to about 70 degrees or so. Which is why, like, even though this is really hot, it's got to be a little bit hotter to work even better. So I'm going to pour this out into this glass. And this glass of water, I'm going to put a large ice cube in. And you can see the level of the ice, like, because ice is less dense than water, it's a little bit above the top. And what we're going to check as the ice cube melts is whether when it melts, the level of the water goes down, whether it goes up, or whether it stays the same. And it's quite near the 350 mark, but I'm going to mark on it with a marker, just so it's a little bit more evident.
The water with it's hot water, huh? In the both in the glass, it's hot water.
Yes.
Okay.
Does this marker show up on the camera, or should I get a darker marker?
A darker one, please. Wow.
Okay, so this is the level of the water there. And we're going to see whether it goes up, goes down, or stays the same level. Okay, there we go. When the water is nice and hot, so we can see the balloon's fairly inflated because the acetone, the acetone boiled. And just holding it out, over the course of a couple of seconds, it's cooling enough. You can see it shrinking right before our eyes. So it's going back into the liquid stage. And one other reason why I didn't ask you guys to do this one at home, I'm smelling acetone because the rubber of the balloon, especially when you're getting it hot, it's not completely, like it doesn't completely seal in the acetone. So some acetone vapor gets out. If you're
So
not
you're
in a
telling
world
me
that,
that you put like nail polish remover in the balloon?
yeah, exactly.
Yeah, you need some idea to do that.
Yeah, well, I got the idea for that from a teacher in Spain. There's a really cool group of science communicators. They're called the DDD, which it's Spanish for disfrutar, divulgar desinteresadamente, which means discover, kind of like share science. It's like science popularization is divulgación científico in Spanish. And desinteresadamente means like without gaining money. So they're teachers who do it for fun. They do it not to get any money from it. But they have a lot of cool ideas for different experiments you can do. And because the ice cube hasn't fully melted yet, I'm just going to repeat one more cycle of that.
Why does it go up, like grow? Because there's acetone in it. I know, but why? How?
So acetone, as I had said a moment ago, the boiling point of acetone is about 54 degrees Celsius at regular pressure. Inside the balloon, the pressure is a bit higher. So it might be something like 60 or 70. And so it boils inside. And I don't know if the microphone picks it up, but when I pour the water on it, there's a hissing, which is actually boiling, like similar to when you leave a kettle to boil, it'll make a hissing noise. And like here, there's a hissing noise. It's probably not loud enough for you to hear, but like it makes this hissing noise as the acetone boils. And when it's fairly inflated, there's not much liquid inside, and as the level goes down and down, you can kind of hear the liquid sloshing around inside.
Yeah.
And now the ice cube's almost melted.
In the glass, yeah, it almost melted.
And we can see the level of the water. It's stayed so far exactly the same. And that's a good demonstration of Archimedes' principle. And Archimedes' principle states that something floating in water will displace a volume of water with a mass equal to its own. And so the volume of ice with a mass equal to the ice is less dense than water, so it takes up less space and it floats higher. But to float that much higher, it's displacing a mass of water equal to its own mass. And once it's melted, the volume that mass takes up is equal to the volume of the water that it displaced. I guess that's a lot of words to say that like the ice cube, once it's melted, takes up the space that the water.
That's normal.
Well, yeah.
It all kind of depends about how heavy it is compared to how big it is.
Well, yeah. It's density, yeah.
Yeah, exactly. There was a cool thing based on that, basically, where they had basically an object and they wanted to know if it's made of this, and they had the same basically material and the same weight of it. And so they tried lots of different things, and it ended up they put it in the same cup and they saw how far it went up, but it couldn't get that big a thing. And then they ended up putting an ancient weigher underwater with the two things underneath it, and that somehow showed that one was heavier than the other and wasn't made out of the same material.
Can you repeat the last part where they were both? Oh, okay. No, okay. Yeah, I understand. and they were both underwater, and they were looking at the apparent weight underwater, right?
Yeah, and one was heavier than the other, and yeah, it showed it.
And I think one way that's very often told, especially in France or in French schools, is the Archimedes crown story, where it's
That's exactly
to
it.
verify if a gold crown was really gold or if it was a fake metal, right?
Yeah.
And so that's a good demonstration of the exact same thing.
Mm.
Okay, so that was a couple experiments on phase changes, and there will be a lot more phase change experiments coming next Saturday. Now I'm going to move on to some magnet ones. How many of you grabbed the materials I recommended for this one?
Well, I got clips and I got the thing we put on the refrigerator, but I couldn't get magnets.
Okay, but the thing you put on the refrigerator is a type of magnet, right? It sticks to the fridge?
Yeah. Yeah.
Perfect. So the first thing we're going to do is we're going to grab fridge magnets. So I'm going to go over to my fridge and grab some magnets. If you have fridge magnets, then please grab them as well so we can see. Okay, so here I've got a big fridge magnet and a couple of smaller ones. And what I'm going to do is just kind of try and stick them on each other and try and rub them around. And you should notice if you do this yourself, and if you don't have a giant one like me, you'll just be sticking them backs to each other. And most directions they slide smoothly, but there will be one direction where they kind of skip and they go in jumpy steps. And I can show you that with this one kind of sideways. And as I move it to the side, there's only certain places it'll stick and it'll go to certain different bands. The other direction, I can move it up and down any way I want. And if I turn it, it'll stay anywhere I want. But there's one way where it's kind of jumpy going between. Have you guys managed to find that with any of your magnets at home?
Yeah, me, it works weirdly.
Because of anti-polarity or something.
Exactly. It's it's a really weird thing to expect because that's not how magnets normally work. And what it is that the polarity of the magnet switches. So in this example, and most of the time it'll be the long ways of a magnet. So sometimes it'll be the short ways. It really depends. But here, and I guess I could have taken the stickers off so it wasn't distracting, but the magnet is made up of different strips, some which are polarized this way, and some which are this way. And so it'll line up if we do it like that, it will line up when the poles are opposite. But when we try and get it in between, which corresponds to half the width of one of those things, then it won't want to stick there and it'll go one step further, one step closer. And the reason it does that is simply because to manufacture fridge magnets this kind of sheet magnet material, they came up with a way of manufacturing it really cheaply by laying it down in strips. But for the manufacturing process, it needs to alternate which direction it goes. So there's no good reason for the quality of the magnet you get. But an interesting side effect of that is that the strength of the magnetic field gets weaker significantly quicker as you move away from it than a regular kind of magnet. And you can check that if you have something made of metal, like a paper clip. And you can notice the paper clip will stick on if it's right next to it. But if you move it even the smallest distance away, well, if it's too small, it won't work. But very quickly away from it, it's not getting any more magnetic field from it. And so the magnetic field drops extremely quickly because you have the ones that are going one direction canceling out with the ones that are going the other direction. And that's opposed to here I have some really strong magnets. Here's a really strong magnet. And aside from being stronger, its effect on things will weaken significantly less as we increase the distance. And so that's a bit of a curiosity about fridge magnets, but that's also a good reason why fridge magnets don't work the best for the next experiments I'm going to show you. If fridge magnets are all you have, like use them. They're certainly better than nothing, but they'll tend to be fairly weak at anything where you're trying to get force over a distance. Next thing I want to show, I forget if I showed this to you guys with the €1 science before looking at coins, but euro coins, like 1 to 5 cents, they're copper coated on the outside, but copper is not usually attracted to a magnet, and these coins are clearly attracted to a magnet. And the reason for that is because on the inside of them, they're steel. And that's just because steel or iron is a much cheaper material than copper. So to make the coins cheaper, they have steel on the inside, but then they're attracted to a magnet. Can you guys suggest some other materials that you think are either magnetic or not magnetic? Looks like Eli might have his hand up.
It's Gabriel, but I have like an example. If we like take a magnet, and we stick a paper clip to it, and we put a lot of other paper clips, they will stay together because there's the electric field who's gonna pass through all of them. Not, I think, no, like, yeah.
And it's actually a magnetic field rather than electric field, but they're very closely related. So we won't really worry.
Or maybe if you like put like just like a small penny, it will maybe.
How about if I take another metal, like if I take a bit of aluminum foil, and here I just have a foil ball. Is this attracted to my magnet? Okay, that's good, Alex, in the chat. Iron, aluminum, nickel, cobalt, and rare earth elements, samarium, dysprosium, and neodymium all make magnets. That's very true.
And neodymium's the stronger, right? The strongest.
Neodymium is one of the strongest. It's certainly the strongest, like easily commercially available. So like this one I have here that's really strong is neodymium, as well as like this stack I have. So for like reasonably readily available, or like you can buy online, really strong magnets, neodymium is the strongest you'll tend to find. And they have different ratings too. Like
I think I have a neodymium. I think, I'm not sure. Like
awesome. If you do, then it'll work even for the last thing I'm going to demo for you guys. So I'm going to demo attraction of kind of surprising things. So aluminum, it's not ferromagnetic, but iron, nickel, cobalt, and I don't know if neodymium for sure is ferromagnetic before it's, well, it must be. But aluminum isn't. So normally it's not thought of as magnetic. Like I can bring the magnet close to it and I'm not getting any reaction. But with this drinking straw, and I've actually tangled a couple drinking straws together. So with this drinking straw and this piece of thread, and this is something you can do at home if you have a drinking straw and a thread handy, you can hang it to make something called a torsion pendulum. And that's just a fancy way of saying it's something really light hanging on something that spins easily.
What do you do with it? I've got both of these things.
So hang the straw from a thread.
Yeah.
And what I've done now to test the aluminum is I put aluminum on both ends. But like the same setup will be used with different things on the end. And it's a little bit finicky to balance. It doesn't need to be perfectly balanced. Like mine's not flat. I'll make it a little bit flatter. But just by looping the thread around it. And now I'm going to bring my magnet close to the aluminum. going to stop it spinning first. And we find that it's attracted to the aluminum. So I can change the direction and get it attracting back this way.
It's like the how do we call it, the electric thing that you see like when you rub it against your head.
Static.
Exactly, like static electricity, because it's
Yeah.
showing attraction. Another kind of surprising thing, although it shouldn't be that surprising, I'm going to take a Paris Metro ticket. And you know, on the back, there's a strip that we call it a magnetic strip. But because they don't want to use a lot of materials when making it, we can see I'm not able to pick it up with the magnet. So we can't demonstrate the attraction that well. But if I put that at one end of the torsion pendulum, so I'm just going to take a little bit of tape. And now with the Metro ticket, we'll see the Metro ticket clearly is attracted. And a slightly surprising place we can find iron as well is in breakfast cereals. And here I have a box of breakfast cereal. And if you
It's
look
that
online,
easy, science, to find some stuff for science. It's that easy.
Exactly.
It's like everything you can find.
And the very last ingredient, and it's okay if it doesn't like show up that well on the camera, although it seems to show up okay.
Mm-hmm.
Yeah.
In French is fer, which in English is iron. Iron's a magnetic material. I can see it only has 8.3 milligrams per 100 grams. So that's less than 1 gram. But that's enough with the torsion pendulum to be able to see it. So I'm just going to take like 3 bits of cereal. And I'm going to tape this onto this straw. And we should be able to see it attract.
Voilà, c'est pas so utile. Ne me regarde pas comme ça. Le micro, il est... T'as quoi dans le cerveau, ouais?
And now from the iron content, I should be able to demonstrate attraction of breakfast cereal to my magnet. So it'll follow the magnet along. And I can change direction. Should be able to change direction. And generally this will work better with like sugary cereals, which are marketed more for children. And the reason for that is because a lot of it is made with like plain white flour and ingredients that are often fairly low in nutrients. So then it's either recommended or sometimes mandated by law that they fortify the cereals with essential nutrients. Iron's a really easy one to do because all they need to do, and it sounds kind of surprising and maybe even slightly disgusting unless you think about it, is if they grind up really small bits of iron, we can digest that in our body and we can get our iron content just from little bits of iron. So breakfast cereal contains little bits of iron, and you can actually do messier experiments to take the iron out of it.
Why is there metal in cereal?
Why is what?
Why is there metal in cereal?
Well, because iron is a nutrient that we need to eat. Where it goes in our body, most of the iron goes to make red blood cells that carry oxygen. And so if we don't have enough iron, then we have iron deficiency and we have problems transporting oxygen to our muscles when we need them. So we need to consume iron. Usually
it's just like weird to say that there's metal in cereals.
Yeah. But there's usually not bits of metal in cereals that are marketed for adults, because if they're not adding sugar to it and they're not marketing it for kids, then usually it's not seen as they need to add extra nutrients to it. So
So
it's
what?
like it's kind of weird. I think why I bought this box of cereal, because I don't actually eat cereal like this myself, or at least very rarely, but I think I bought it for experiments. And now, because I've had it a long time and it's getting near the expiration date, now I'm actually eating it sometimes, so I don't throw it out. But like it wouldn't be my first choice, but I bought it because I was in the store and I was looking at what children's cereals had the most iron, so that I could do this experiment, and that this one had the most.
Yeah, it's good, but it's really, really sugary. You have to mix it with other stuff.
But maybe I should try mixing it. Maybe that's the problem. And we've gone over time, so I just want to finish with like one other application of the torsion pendulum. And this one doesn't work extremely well. You can probably see this isn't like metal or cereal at the end. It's bits of carrot. And this one,
Carrot?
yeah, carrot. And this can work with any fruit with a high water content. Like I think I recommended grapes or similar fruit.
I've got tomato.
That should work. I have some cherry tomatoes here. Sometimes that backfires.
So do we just stick it on the end?
Exactly. Just stick it on the end. Like I poke the straw through it. If it won't stay, like feel free to use tape.
But if you poke a straw through a tomato, it might be a bit messy.
Let's see.
Yeah. So do it like over a plate or somewhere that might.
Most of the juice will stay in the straw. Hopefully.
Oh, done. Yes, that worked.
But for this one, this is about 100,000 times weaker than ferromagnetism. So it's going to be weak enough, unless you have really strong magnets, it's probably not going to work. So if you have a strong magnet,
No, it's like when you put to like charge something, you can do it with potatoes.
Yeah. And
I learned that.
What should happen here? If we're lucky, it should very weakly repel it and push it away.
Okay, wait, coming back.
So I'm just barely getting any movement there. Like that's not enough to be really convincing it wasn't just moving on its own. Like because of the string. I'm going to switch one end for a tomato. But the problem with tomatoes is the water in them could demonstrate diamagnetism, so that could cause it to move away and be repelled like we're hoping for in this demo. However, sometimes the iron content in tomatoes makes it so it's actually attracted. And tomatoes don't have a lot of iron, but because ferromagnetism is 100,000 times more sensitive than diamagnetism.
Wait, did we pass the time?
Yes, we did. And so this is the last demo, and now we're done.
So when is the next class? 2 weeks.
The next one is on Tuesday, and it's being guest hosted by School Lab at CERN in Geneva with my friend Anya and her friend Sarah. That one's going to be like they'll be performing, like I guess you could say, and showing how a cloud chamber is made in the end, but doing it
clouds is pretty easy to know what it's made of.
Yeah, but a cloud chamber is kind of a way of making a cloud in a box, and then you can detect subatomic particles from it.
The tomatoes are really, really moving. They're really.
But are they attracted or repelled?
Repelled.
Awesome. So then that's working. That's exactly what should happen. And it's surprising because usually we're used to only seeing ferromagnetism where it attracts, and we're not used to seeing things repel. So that's great that that's working well.
Those ones are certainly being repelled. I've tried switching and it works.
That's awesome. It's working better than mine is. I'm really happy it's working for you. Okay, so just to recap before saying goodbye. So Tuesday is the science show with Anya and Sarah from CERN School Lab.
And then
I'm
it's
really excited for
Saturday.
it. What's that?
And then it's next Saturday.
Next Saturday, and that one I'll be going over phase changes. So similar to the acetone in the balloon and the ice cube, I'll be asking you guys to have a fair bit of ice. So try and have like 10 or 12 ice cubes ready for that. Salt and a thermometer would be good to follow the experiments at home. Then the next week, there's Jeff, who's the head of teacher programs at CERN. He'll be explaining what CERN is and the research that goes on there. Then the following one is Luka from Serbia or Slovenia. Like he's originally from Serbia, but he works in Slovenia. I don't know where he'll be at the moment, but he's doing one on coins and science of coins.
Didn't we already do coins?
Yeah, but there's a lot of stuff we can do with coins. Like I also used coins today. But with that, I'll conclude. Thanks for joining me again. If you have more questions, feel free to stick around and ask more. But I've already gone later than I expected. So have a great evening, and I hope to see a lot of you on Tuesday, or if not, on Saturday.
No, well, I'm not going to be here to Tuesday.
I'm also not can't be here on Tuesday.
Is there one of the Tuesday that's going to be really important?
Really important. Probably not important in the sense that, like, if you miss it, you won't understand the next sessions. Like most of the sessions, you should be able to attend any of them, regardless of how many you attended before or not, and they should still make sense. One exception to that is Tuesday, February 2nd, which is a month from now. That one has a little bit of electromagnetism where if you don't attend the session I run beforehand on electromagnetism, then you might have a harder time understanding it.
Just saying, I'll be here on all of them except the one on the explaining of CERN. I think that's Saturday.
No, that's Tuesday the
Tuesday.
19th.
Yeah. Won't be there then.
Okay.
Well, I'm supposed to be only Saturdays.
I'm also only Saturdays because I can't Tuesdays.
Well, I'll be here next Tuesday.
That makes sense because you guys are a little bit younger, and the Saturday ones are like best if some of the stuff on particle physics might seem a bit complicated for you. So like the Saturday ones, we should always be doing experiments with things around home. I don't have any exceptions planned. Something might come up like in February, but all the Saturday ones will be with experiments where you'll be doing things rather than just like listening or answering questions.
Okay.
Does anyone else have any other questions?
No. See you on Tuesday.
See you on Tuesday.
See you
or
on Saturday.
for something. Thanks
Bye.
again for joining. Have a great evening, everyone.
Thank you.